Hello and welcome. We're going to look at how the equilibrium constant varies according to the way we write the chemical equilibrium. So it's always very important to have the chemical equilibrium written out before you can make sense of an equilibrium constant. For instance, imagine we've got a reaction A plus 2B is in equilibrium with 3C. And we can write an equilibrium constant, Kc, and that would be the concentration of C cubed over the concentration of A times the concentration of B squared. And remember, we're just getting these coefficients here and we're raising them to the powers here in the equilibrium constant expression. Now, we can do a couple of things to this equilibrium to change it. So, for instance, we can reverse it. So we can write the reaction backwards. We can consider 3C in equilibrium with A and 2B. And that gives us a new equilibrium constant. We'll call it Kc prime. And it's going to be equal to the concentration of products raised to their stoichiometric powers over reactants raised to their stoichiometric powers. And you can see that's really exactly the same as the one we have above. It's just turned upside down. So in general, when we reverse an equilibrium, we invert the equilibrium constant. So that's the very first thing we've got to remember with equilibrium constants. When we write a reaction backwards, we invert the equilibrium constant. The second thing we're going to consider is what happens if we multiply an equilibrium constant by a factor. So let's go ahead and multiply it by a generic factor n. So now our equilibrium would be Na plus 2Nb is in equilibrium with 3NC. So if n was 2, right, we'd have 2A and 4B and 6C and so on. So now our equilibrium constant, Kc, I'll put double prime because I've already used Kc prime, would be equal to the concentration of C to the 3N over the concentration of A to the 1N times by B to the 2n. And in fact, we can see that is exactly the same as the original equilibrium constant. We have just raised it to the power n. So when we multiply a chemical equation by a factor of n, then we raise the equilibrium constant to that factor of n. So whatever you pick, right? So if you double it or triple it, then you square or you cube the equilibrium constant. So that's the second thing we've got to know. So let's move on to the third thing now. Now, the third thing is going to be what we do when we take two equilibrium and we try and sum them together. So imagine we've got an equilibrium A and 2B, and it's got an equilibrium constant. We'll call it Kc1, and, well, maybe you should pause the video and write it out. Okay, so it is B squared divided by A. And you take another equilibrium, so maybe it is 2B is in equilibrium with 3C, and so it's got an equilibrium constant. We'll call it Kc2, and that's equal to, you want to pause it and write it? Okay, unpause it. It is C cubed divided by B squared. Okay, and now we're going to go ahead and we're going to add these together. So the third rule is what happens when you add the equations together. So when you add them up, right, you're going to have A and 2B in equilibrium with 2B and 3C. And just like we did in the first semester, whenever we've got things on the left and the right, we can cancel out and we can write the equilibrium constant for it. So we'll write that in green, why not? So the equilibrium constant, Kc3, is equal to the concentration of B squared times by C cubed divided by the concentration of A times by B squared. Okay, so where am I coming from? Well, I've ignored the cancellation here just for a second, just to kind of point something out. And you can see before I've canceled out, I essentially have my original equilibrium constants. So B squared over A, well, it's this thing up here, right? This is just Kc1. And if you look at the second thing, right, that is C cubed over B squared. C cubed over B squared is right there. That is Kc2. So you can see when I add chemical equilibrium, we multiply the equilibrium constants. We'll find that's very, very helpful later on. So we can couple reactions together. We can take a reaction that has a small equilibrium constant and couple it to a reaction with a really large equilibrium constant. And when we multiply them together, we'll get an equilibrium constant that's favorable. Our body does that all the time through hydrolysis of ATP, which has a really high equilibrium constant. We can drive reactions that might otherwise not take place. Now, in terms of the cancellation, you might say, well, wait a minute, you were supposed to cancel those b's out. And you can see in my equilibrium constant, if I had a b squared up top and a b squared down bottom, they would cancel out. So the only thing that would really be left with would be c cubed over a. So c cubed over a. So it does actually work out, but I probably was a little too hasty cancelling out with my yellow pen. So pretty awesome. So adding equilibria, you multiply equilibrium constants. We saw that multiplying equilibrium reactions, we raise the equilibrium constant to that power. And when we reverse an equilibrium reaction, we invert the equilibrium constant. So now we are experts at manipulating equilibrium constants, right?